Hi, this is a small video to show my most ambitious finite element code so far. So it's about structure modelization. We take as input, so this is the main function. It first reads by the call of geomet the structured frame. A frame is a structure like this, where we just enter as input the nodal coordinates. So for frame 1 that we're going to test first, we have a beam with one node in 0, one node in 3, one node in 6. So it's a horizontal beam, and all connectivity, because there are beams, rigid links, stuff like material stuff, and restraints, and also displacement. So imposed displacement can generate constraints. We can have a spring on one of the nodes. We can have a concentrated load, of course, a distributed load, temperature variation, and pretension. Pretension is like in reinforced concrete when you have a wire in the concrete, so it can also generate tension. Okay, so let's try it. Let's call the main function. We'll call the read of the file name, then we will solve it by call of mkk. Mkk produce for every element in the structure the stiffness of the element, and also it's a matrix stiffness, and also the forces, so they are equivalent to the loading that is applied on the element. So it basically takes the loading and thinks as, okay, I am an element alone, and what applies on my nodes instead on the element. Okay, then once we have the stiffness and the equivalent nodal forces, we assemble it into a global stiffness and a global equivalent nodal forces, and we can solve the system by the use of linsolve for a symmetric and definite positive matrix as Vk, who is the stiffness. Okay, and then once we have called this, we have the displacements, and there is deformed shape to make the rendering. So it's also a function that represents the nodal coordinates, not the rotations. So it's not really realistic as a view. We can get the rotations on the nodes, but we don't display them. They are just readable in the output. So we'll see it later, and it's just about having a glimpse on how the structure should behave. So if I call a main for, let's say, frame 1, we can see that it makes a calculation, and we have our beam of 6 meters long with 3 millimeters vertical displacement. Frame 2 is the same, but with more nodes, so we should have something more that fits the motion of a real beam, so it wouldn't do such a thing, but more with more nodes, it's a little bit more like this behavior. So we have the same displacement of 1 millimeters to the down, and we get the 6 meters beam motion with the same load. Frame 3 is a triangle that is loaded with vertical loading. As we can see, we have just a concentrated load on the node 2, so in the middle, and you'll see that it's a little bit more stiff. Frame 3, it's stiffer, and also this is in meters, so we don't see much of the motion on the node, but there is one, as we can see if I do a clear. I'll call it again, so we get a view of it here. Yes, displacement. So this is the rotation of the first node, horizontal displacement, the second vertical displacement. So it's about 0.4 millimeters. These are millimeters, and all the rest of the displacements as well in our elements. Okay, so I'm going to show last. My last frame, it's a custom one. It's a Maison Caoutchouc, because I made it very flexible. If we look at it, so it's with more nodes. It looks like approximately a house with some dispositive against the wind, and we have a distributed load which corresponds to the left facade. So the left facade is a little bit loaded. We have a concentrated load on the node 4. Which one is it? 1, 2, 3, 4. It's in 4, 8, so it should be quite in the middle. And we have a temperature variation, which is it's on the element 5 and 6, so it's the right facade, and it's not differential. It's, yes, it's just it should reduce a little bit and flex also the elements with this. So let's run it with the frame maison caoutchouc. Frame maison caoutchouc, perfect. Up. And as we see, so we have the loading on the left facade. We have, I think, on this node, yeah, this one is a little bit lower than it should be because there is a vertical loading, and we have the temperature variation that we don't see much as well, but it takes it into account in the calculation. We can see that the facade, the rightmost fiber of this facade is a little bit shorter, and it flexes a little bit. There is a little deflect in the either. For those who are a little bit more curious about Maison Caoutchouc, we can see that it's caoutchouc because the characteristic here is it's a very low Young modulus, so it's very flexible. Let me add 1 0 to see how it behaves. It should be way less flexible if we test it like that. Frame 3 again, yeah, frame Maison Caoutchouc, and there is less deflect in the shape. Also, it's interesting to note that this node is pinned, so it doesn't move. It didn't move neither horizontally or vertically. This one is only fixed vertically, but there is a horizontal displacement as well. So I hope this code was nice for you. I know that there are some more professional codes that did it, but I really implemented it for fun and for also for once creating a full finite element code that produces some suitable results. So I hope this one was nice to watch, and I hope I will come sooner with more content. Bye!